Hello, students. Today we want to talk about more theory of the derivative. We've discussed the definition of derivative and many theorems that allow us to compute derivatives. And then we talked about the topic of the implicit function theorem, which allows us to differentiate implicitly, which again gives us more power when we're trying to compute derivatives. So we find that when we do the implicit technique, we can compute the derivative of a function without having an explicit expression of the function. And that is very, very powerful. You will appreciate that technique more as we move through the course. Now, today, as we begin more theory of the derivative, we want to talk about the extreme value theorem and Fermat's theorem. Both of these theorems are fairly straightforward to use. You will find that just like with all of the other results, you will do the requisite algebra and differentiation and then analyze what you've done to make conclusions. So this will remind you basically about what you've already been doing in the class, but actually give us more power as we work towards using the derivative to fully understand a function in terms of its graph, when that includes shape, increasing, decreasing, maxima, minima, things of that nature. And the maxima and the minima allow us to venture into the area of optimization. Again, the power of the calculus is really useful to us. And if we think about what we've been doing before, we can always use our intuition to get to what we believe to be a good conclusion. But now the calculus will give us the last piece of the puzzle. That is, we don't have to guess anymore. We don't have to just get by with doing what we can. We can finish the story, so to speak. So let me share my screen so we can talk about a few of these new theorems along with some of the requisite definitions. Now, what we find in this particular case is with the extreme value theorem, there is nothing new here. You will not be surprised by this result because we know about continuous functions. But first, what we want to do is just, before we state the theorem, is to give a good solid definition of a maximum and a minimum of a function. So what we're going to do is start with a function defined on an interval I containing the point C. Okay, and so we're going to say that the value f of c is the minimum of f on I if and only if f of c is less than or equal to all other values of f of x where x is contained in I. So again, this appeals to your intuition and also appeals to the definitions that you wrote in your previous classes. And again, one thing that books will often do when you refer to a minimum, they will often say absolute minimum. That is, we're not talking about relative or local, we're talking about absolute, that it is the smallest value of the function for the given set. Now, the opposite of this would be to define the maximum. So again, remember the maximum or the minimum corresponds to the value of the function, but they often are written as an ordered pair. That is to showcase where the actual C is. So do not confuse the maximum and minimum with the ordered pair. If it is required to be stated that way, that is only to provide more information. The actual value of the function stands for the minimum or the maximum. Now, of course, the maximum of f on I would be the f of c being greater than or equal to f of x for all x in I. So again, we refer to values of the function as being an absolute maximum or absolute minimum. And of course, if you leave out the absolute, it doesn't matter. It maximum, minimum means the same thing. Most authors are trying to focus on the difference between the relative minimum or relative maximum and the max and the min by just adding the word absolute. And it is helpful. Now, what we know is that when we computed limits earlier, we were always very happy to have functions that were continuous, because continuity gave us a very powerful result for computing limits. If the function is continuous at c, then the limit as x approaches c of f is simply direct substitution. We simply evaluate the function at c. So I don't think this result that we're going to give now will be a surprise to you. Now, the hypothesis will require a closed set. Now, sometimes I will say closed comma bounded interval. The real line is both opened and closed. So many authors will say closed and bounded. But for our work in this class, if you're given the hypothesis of closed, you can make the assumption that you have two distinct endpoints that define the closed interval. So again, you may not see the word bounded, but if I say it, we are assuming that we are dealing with a closed interval of finite length, where you would just say the right endpoint minus the left endpoint to get the length of the interval. So if we start with this and we have a continuous function, then the result is that f attains a maximum and a minimum on the set AB. Now, the proof of this you will find in the notes. It's sketched out very cleanly and is very, very doable. But at this point, I want you to be able to understand the use of the theorem. And then as you get more comfortable with it, go back to the notes and check on some of the topology that we use to prove it. It's very straightforward, but again, I want you to get comfortable with actually using the result. Now, again, when we think about a continuous function on a closed bounded set, we see that all the limits are computed by direct evaluation. So we can't even think that the function would ever be unbounded because we are including the endpoints. We can check every value on the given set by direct evaluation. So the idea that the function actually attains a maximum and a minimum is not too far off from us, because we first, if we are to prove this result, is to show that the continuous function on the closed bounded set is indeed bounded. And then using the supremum property of the real line, we can actually show that the max and the min are attained on the set. Again, those are very straightforward arguments, but do not focus on them initially. Use the theorem, then go back, check your lecture notes, and I think you will find that it'll be maybe a little bit easier to follow. Now, when we think about the conclusion of the theorem, what that basically means is that there are two elements in the closed set. We can call them alpha and beta, such that f of alpha provides in this case, the minimum. That is, f of alpha is less than or equal to f of x for all x in the closed set AB. And then there's a beta such that f of beta is greater than or equal to f of x for all x in AB. That is, f of beta is the maximum. Now, again, not a surprise, but this theorem doesn't say anything about how often a maximum or a minimum would occur. So again, don't make any inferences about that. And then number two, it doesn't really tell us what we need to do to find them. Okay, so that's when we need another result to actually assist us with the pursuit. What we're going to find is that the Fermat's theorem will give us the additional ingredients to understand what happens on the interior of the set. That is, are there elements in the interior away from the endpoints AB that provide us additional information? And then what we will find is that the calculation of the values at the endpoints with the additional information from Fermat will give us all of the information that we need to determine the maximum and the minimum and where they actually occur. So that's why when we study the calculus, we combine the EVT, or the extreme value theorem, with the Fermat's theorem. Now, of course, we're going to need a little bit of extra stuff to quote the Fermat's theorem. So let's do that. Now, as I said before, we have the maximum and the minimum. And what we need to do is talk about the concept of a relative extremum. And I've got these in the notes. You can see the conclusion of the EVT proof here, which is very doable. Again, save that until you've had a chance to work with this. I'm going to do some examples so that you can get very familiar with the use of these theorems. Now, some of you have read books where instead of relative extrema, you see the terms local extrema. Those are synonymous. Relative, local. So again, what we're thinking of in this particular type of setting is that if we are close enough in some open set about C, then C will take on the max or the minimum, but it is relative to that set. It is a local phenomenon. So if you would rather use local instead of relative, that's fine. I will try throughout the course to use the relative term, since that is what our book is using. But you feel free to think of this as local extrema. Same thing. Now, what do we mean by the relative maximum, f of C being a relative maximum? That just means there is an open set I containing C on which f of C is a maximum. Okay, so like I said before, you can think about an open set about C. If you like, you can just think of a little delta neighborhood, C plus delta. We'll use this in the Fermat theorem. I'll be able to go through a couple of steps with that proof because it's a little bit more straightforward than the EVT. So we can think of delta as being a positive tolerance, just like we did with the definition of limit. And so in this open set, we can call this I, if you will, based on the definition. We would say that f of C is a relative maximum if f of C is actually the largest value on this set, that it is greater than or equal to all other f of x where x are contained in the open set I. So again, we just refer to the definition that we did for maximum without having to write the definition over. Again, local, relative to an open set. So you can think about the graph of a polynomial that might have many peaks and valleys. And so if you think of the peaks as being relative maxima and the valleys as being relative minima, because you know if you do not restrict the value or the domain of the polynomial, the end behavior will allow infinity or negative infinity or a combination, whatever. The thing is that you do not have the absolute maximum. You do not have necessarily the absolute minimum. Now, of course, if you've got an even degree polynomial with a positive leading coefficient, you know the end behavior would be this. So it may very well be able for you to determine an absolute minimum. Okay, so this, again, we always have to think about what the hypotheses are. If we start to loosen them, then we don't get the guarantee that the EVT gives us. For instance, the EVT requires a continuous function, and the EVT requires the compact set. That's often the term used for closed and bounded. If you start relaxing that, then the guarantee is not there. You may very well get the max and the min, but it will not be guaranteed. So keep that in mind. Think of continuous functions with vertical asymptotes that tend to infinity, like 1 over x. If you have an open set 0 to 1, then you don't get the result, do you? You don't get the result. Well, and you can't include the endpoint 0 because the function is not defined there. So as you think of the EVT, think of the fact that all of the hypotheses are needed. Now, again, just to mention one more thing, if we were to talk about the relative minimum, as I referred to with the polynomials, we would say that f of c is a relative minimum if it is the smallest value when x is contained in the open set I. So again, like I said before, just think of your friendly neighborhood polynomial. Maybe has something like this. Maybe does something like that. And then you could see here a relative max, a value of relative minimum, relative max. So this is what I'm referring to. Locally, and so you could think of this as a C1, where you have a open set about C1. You can think of this as a C2 and an open set about C2 and a C3 and an open set about C3. So this would define 2 relative maxima and 2 relative minima. So we'd say F C1 relative max, F C2 relative min, and here F of C3 relative max, just using very simple abbreviations. So locally, we can talk about extrema being the plural of the extreme. So again, you're thinking, why do we bother to do this? Well, of course they exist, and you made these definitions when you took your prerequisite courses, but they are important in the theory. So before we state Fermat's theorem, which will actually involve the term relative extrema, we need one more definition. And this definition will not surprise you at all. It'll probably give some credence as to why I factor things and look for zeros of derivatives and look for real numbers or domain elements for which the derivative is undefined. There has always been a purpose behind that, whereas you might think, well, why does the professor neaten up the problem so much? What is the reason behind that? Well, this very definition gives us a response. So let's just assume that f of c is defined, okay? That c is in the domain of f. So when we say this, we say c is element of the domain of f. So many times when you do a calculus problem, it's always a good idea to state the actual domain. The domain may be given in the problem, or you might be doing a word problem where you have to figure out a domain that makes sense. And of course, if there is no domain provided, then you will look for the largest possible set of real numbers for which the output is real. So that would be the type of question you would have had in the prerequisites, where you had to determine the domain, which usually meant 2 things: no even nth roots of negative numbers and no division by 0. Those were the rules that you would have to apply so that you could come up with a correct domain. Now, what we want to do is to find a critical number of f, and it's very easy to do. We've been doing this, but we never called the elements in the domain of f a critical number, but now we actually know that we've been computing them. The first part of the definition means that f prime of c is 0. So if we compute the derivative of a function and we find its zeros, then we have determined a critical number. Of course, the critical numbers must be in the domain. Okay, so when we identify a zero of the derivative and we're like, okay, that is an element of the domain, we have a critical number. It is important to make sure that if you designate a critical number, that not only in the first part is f prime of c 0, but c must also be in the domain of f. The second one that occurs maybe less often, but is actually quite important, is f prime of c is undefined. And what that usually means is a construct where you have division by 0. Now in many cases, when you compute a domain and you have division by 0, that phenomenon pretty much is transferred to the derivative. And so when you see that the derivative is also undefined at that number, it does not become a critical number, clearly, because it's not in the domain of the original function. However, if the behavior or the characteristics of the function create an undefined number in the derivative that did not exist in the original function, then you do have a critical number. So that's really important. We always have to make sure that we are staying in the domain. For instance, if we have square roots, then we know that we can't include any numbers that will provide an imaginary output. So that's usually never a problem for us. But again, just remember, when you state a critical number for a function, the critical number must either provide f prime of c is 0, where c is the critical number, or in this case, f prime of c is undefined, and c must be a domain. Now, it's going to take some time to get used to this, okay? Because it's a little odd, because we haven't done something like this, at least in a formal sense. Just remember, we are looking at f prime of c equal to 0, which is basically just solving an equation, which you know how to do, and looking for real numbers in the domain for which the derivative is undefined. So these will be the two critical parts, and basically three critical parts, because we must have an element in the domain. So that defines the critical number of a function f. Now, as you've noticed here, I've written Fermat and I've said combined with EVT, and that's what I spoke of earlier. The combination of the two theorems will give us a very powerful evaluation tool. And so what is Fermat? Fermat is the mathematician who wrote this theorem. He was one of the greatest mathematicians in our history. And we often just refer to this result as Fermat's theorem, or I'll just call it Fermat. But of course, there are lots of famous results attributed to Fermat. The one in number theory, Fermat's last theorem, or whatever. So I'm referring, when I say to Fermat, this result in calculus, and it is very simple to state. If the function f has a relative extremum, that is a relative max or min, then it must occur at a critical number of f. So when we think about something like this, the C1 is a critical number, at least intuitively, because it defines a horizontal tangent. So when you think of the tangent line here, you think horizontal, horizontal, horizontal. Or we could have a cusp where the function would be undefined, like x to the 2/3. And we end up having a minimum of 0, absolute, that occurs at 0, where the function derivative is undefined. So this is not a surprise. It is not a surprise when you think about the geometry of the situation. That is, and it's easy to state, if f has a relative extremum, that is, and you could think, well, you might have to do a left or right derivative if you have something occurring at endpoints, that can venture into the picture. But usually we're going to be looking at situations where the approach can be accomplished from either side. And so now what we see is if we think about Fermat, we take the function, look at its domain, we compute the derivative, and then we look for zeros. We look for horizontal tangents. We look for this, okay? And we also look for this. And then we write a list. And of course, there is nothing that's guaranteed that these will exist. But when they do, we make a list, just like we're thinking about BVs, boundary values for inequalities. And then the EVT will provide the last piece of the puzzle. We will normally see the critical numbers falling in the so-called interior. And then if they do not include any of the endpoints, we will have to move out to the endpoints, because the Fermat will cover whatever's on the interior, possibly an endpoint. And if they're not covered, we check them. So with EVT and Fermat, we can find for a closed bounded set the maximum and the minimum. And you might be thinking, well, the maximum could occur on the interior, or it could occur at an endpoint. The minimum could occur on the interior or at an endpoint. So this is a very powerful tool. And again, it does require, what does it require? Number one, a continuous function. Well, and then plus that we have differentiability. That's another really powerful thing that is required from Fermat, because the critical number demands that we have at least some differentiability to be able to compute number one. And so with that closed bounded set, we have a powerful tool to figure out absolute extrema, or maxima and minima, for a continuous function on a closed bounded set. So one thing I want to share with you is just a very simple idea behind the proof of Fermat. It's I'll go through one of these steps here, and then you can look at the second part as you get more practice working with these theorems. And then after this, we'll do some examples. The reason I like to talk about this is because it's very straightforward and more in line with what we've been doing. But like I say, as you get more experience, go back and look at the proof of EVT, and I think you'll find it to be very illuminating. Now, one thing about Fermat's theorem is that it relies upon the law of the trichotomy. For instance, if we're trying to show that we have a critical number, we've got two cases. And so before the law of the trichotomy, we just might assume that f prime of c does not exist. For instance, if f has a relative extremum, boom, we have a relative extremum. And then we look at case one, which says, what if f prime of c does not exist? Okay, then we're done, because that defines what? A critical number. So students often look at the first case and say, well, yeah, that's quick and it's easy, because that is really one thing we have to consider. That's what we call the easy case, because it's merely just a play on words. I mean, it could be the case that f prime of c does not exist, like we see with f of x equal x to the 2/3, that very famous function that has the cusp at 0. Now, the other case would say, okay, well, f prime of c does exist. We need the law of trichotomy. So when you take a real number, there are three categories. We can think of the number as being less than 0. We can think of the number as being equal to 0. And then we can think of the number as being what? Greater than 0, negative, 0, or positive. So what we would want to do is to eliminate the positive and the negative, and that would only leave the conclusion of f prime of c equals 0. Then that would fulfill the definition of what? Critical number. So let me just go through one of these steps, and then later on you can go back through this and see how straightforward it is. But I like to cover this initially because it is really quite simple and based on just inequalities. So what we want to first assume is that we're thinking of the fact that f prime of c would be positive. And of course, by continuity, this is called preservation of sign. And I've mentioned this before, but if you actually looked in your notes and the first practice test, you saw the proof of preservation of sign. Now, what that means is that we can find a very nice symmetric neighborhood. Remember, I was using the delta before. We can say we can go delta on either side of c, where the actual sign of the derivative would be preserved. That would mean that the difference quotient, f of x minus f of c divided by x minus c, would be positive. So that's what continuity does for us. We don't just become, a continuous function doesn't just become positive spontaneously. It doesn't do it in isolation. It does it over a set of content. So we don't just have, you're running along, boom, you're positive for one point, and then again you're negative or whatever. That doesn't happen. It's always through a set of content. And that is what we rely on when we take the calculus. We need the continuum property of the real line in order to get close to numbers. Usually we like doing it from either side, but still, as long as we have one approach, we can do some calculus. So what we do is we simply take x on either side of c. That's all we have to do to prove this result. So if we take x to be to the left of c, then of course x minus c is positive, and we need to preserve this. So, excuse me, x minus c is negative. So again, we need to preserve this difference quotient. Okay, well, if x minus c is negative, for the quotient to be positive, the numerator must also be negative or less than 0. Okay, because again, the negative divided by the negative, using the properties of real numbers, would give us the positive result. Okay, then of course, if we transpose, that says f of x is less than f of c. Well, then of course, then f of c being greater than f of x would mean that f of c is not a relative minimum. That would be our conclusion. Very simple. And you might be thinking, well, why is that going to help us? Well, let's look at x being to the right of c. That is, if x lives between c and c plus delta, as we have here. This notation is so convenient, and it gives us a recipe to do the proof without any difficulty at all. Okay, so now, of course, if x is to the right of c, the quantity x minus c will be positive. And then as we look up here at the difference quotient, that would mean that the numerator must also be positive. So f of x minus f of c is greater than 0. Now, if you transpose, again, you'll see that f of c is less than f of x. Okay, so that says f of c is not a relative maximum. Okay, well, between the two of these, it's impossible, because in one case, it's not a relative min, so it must be a relative max. In another case, it's not a relative max, so it must be a relative min. Well, those are in opposition. So that case is not going to happen. It's not going to be the case that f prime of c is positive. Now, just using the same argument here, you can show that f prime of c is not less than 0. And then again, by the law of trichotomy, the only conclusion would be is that f prime of c equals 0. So take some time to go through this once you've done some practice with these two results. And I think you'll find it to be very straightforward. And again, the reason that I tend to focus on this form of the derivative, because arithmetically, it provides us so much flexibility when it comes to doing these types of proofs. Without it, it would be more difficult. So this form of the derivative has turned out to be a great bonus to us, especially when we talked about the proof of the chain rule. It makes the proof so much more straightforward. I believe in providing an effective validation of a proof using ideas that connect and make sense. Unfortunately, there are times when you've got to introduce some techniques that may be a little bit more difficult, but are required only because they're necessary. A proof that is just unnecessarily difficult and not required is not always the best approach. We only need the additional difficulty when we have a need for that when it is required. Just like when we talk about the supremum property when we try to prove EVT. So again, we only want to introduce enough difficulty so that we can get to the conclusion in a mathematical way that is legitimate. Okay, so let's look at some examples. Now, like I said before, these examples will remind you more of what you've been doing. So like, for instance, in the past, when you'd have to compute a derivative, when you'd have to compute the equation of a tangent line, maybe you did an implicit derivative, maybe you considered finding a tangent line to the graph through a point not on the graph. That was a fairly interesting problem. Using the definition of derivative or continuity. Now we're going to do the similar thing, but we're going to focus on the relative max and the relative min from Fermat, and then throw in the EVT to bump it up to max and min, absolute. So here's an example that we want to start with. And this is, I think, will be good for us. So we will start with the function y equals 3x to the 2/3 minus 2x. And again, if we're going to use the EVT, we must have the closed bounded set. So again, we cannot do the combo of EVT and Fermat unless we have two very important ingredients. Notice we have x to the 2/3 power, which has no problem with negative values of x. And of course, we have 2x. So this indeed is a continuous function. It's continuous for all real numbers, actually. We can take the cube root of any real number because it does not we're not impaired by the cube root of negative numbers, since that indeed is a negative number, which is real. So what we've noticed here is we have a closed bounded set -1 to 1. And so we have a continuous function. So let's write this down. Continuous on -1 to 1. So I'll just type up here, y is continuous on the closed bounded set. So that provides what? EVT. So what we want to do is compute the maximum, and I'll just say max and min. Now, like I said before, it certainly may be the case that we have more than one occurrence of the max and the min, but we have EVT, so we know they exist. And so we don't have to go on a scavenger hunt and guess and check. We can now apply Fermat with this. So first thing you might do is say, well, Professor Hollis, you said we always really need to kind of look at the endpoints, because if the critical numbers don't give us any idea what happens at the endpoints and we only have interior points, we might as well go ahead and check them. So just as a preview of this, let's just check the values at the endpoints. So we'll say y of -1. This will be 3. So we have -1 to the 2/3 minus 2 times the -1. So now notice this is a twofer. We take the cube root of -1, which is -1, and then we square it, so we just get a 1. So we have 3 times 1. And then, of course, minus the negative just gives us plus. So when we subtract the additive inverse of 2, since we multiply this to get -2, we know that that is just 2. The negatives absorbed by definition of additive inverse. So this just gives us a 5. So we could think of this as an ordered pair. That is, for the input -1, we get an output of 5. And then sometimes in the responses, you are to give the actual occurrence and the value. That is, where does the particular value occur? The ordered pair gives you both. So we know we have a value of 5, and this value of 5 occurs at -1. Let's go ahead and check y of 1. So we have 3, 1 to the 2/3 minus 2 times a 1. Of course, now the cube root of 1 is 1. We square it, we get 1. So that's 3 times 1. And then, of course, minus 2 gives us a 1. So now we have the value of 1 occurring at the input of 1. All right. Now, what's important in all of this is this is certainly a valuable part of the technique. But now Fermat will say, okay, if there are any relative extrema, we must check what? The existence of any critical numbers, because if they occur, they will occur at critical numbers. So let's use Fermat now. So this says y prime equals, so we're going to take the derivative. So we have 3 times 2/3 x to the negative 1/3. Again, multiply by the power, that becomes a coefficient, and then subtract 1. And then, of course, the derivative of the negative 2x will just give us negative 2, the derivative of x being 1. And so now the 3's absorb. So we have 2x to the negative 1/3 minus 2. So when you look at this and you think, when you think about examples like this, the first thing that comes to mind is that, okay, well, I've got this negative power. But no, at this point, you are the driver, so to speak. You are in charge. So if we were to look at this problem, the first thing we could say is that, well, we can set this equal to 0. Because first, what we want to do is see if there are any zeros. So again, we'll just say we're thinking Fermat. So remember, if there are relative extrema, we have to figure out. And then, of course, I've talked about computing the domain. The domain's right there. That's the domain that we use. So we're covered. We have the domain of definition. So the first thing we can do is divide by 2. The 2's are gone. So we have x to the negative 1/3 minus 1 equals 0 equivalently. Now, at this point, you can factor the negative x to the negative 1/3, or you can just write this as a fraction and then get a common denominator. It'd be your choice. So let's do this. If and only if, go ahead and factor x to the negative 1/3. So that will be, in this case, we're left with a 1. And then, of course, we have minus x to the 1/3. Now, if you like, just to make this look a little bit nicer, we can remove this to the denominator, and then we can just factor the negative 1 here. So we'll have a negative x to the 1/3 minus 1. Of course, we could have factored negative of that, but probably easier to do it in 2 steps, and then x to the 1/3. So now we put this in a form that's really simple to analyze. Again, we have to be careful with the algebra, just like we're doing algebra of any derivative, because a slip does change the arithmetic. So we just mind our P's and Q's. So now, of course, we can simply see this. This would say if and only if x to the 1/3 equals 1. And then, of course, we can cube both sides. X is equal to 1 cubed, or 1. So that would clearly give us a 0 of the derivative. And then if we check here, 0 is in the domain, and this is clearly undefined. So here's a 0, and we'll say y prime undefined for x equal to 0. Okay, so again, and remember, we'll just say this is in the domain, right? That's important. And also, let me also note here, this is in the what? This is in the domain. I mean, we want everything to work. We want every number to work, but we have to make sure that we have a number that we find in the domain. The 1 is in the domain and the 0 is in the domain. Of course, we've already taken care of the 1, so we don't have to worry about that, but we need the 0. So now y of 0 equals, now you could also do a table. You could just do a table and list the inputs and do the outputs, but sometimes the calculations might take more space. So you might want to do a summary table if you want, or not at all, your choice. So y of 0, well, that's easy. That would be 0 to the 2/3 times 3 minus 2 times 0, which of course is just 0. So this corresponds to 0 input, 0 output. Now, let's go back up here and compare. Notice the smallest output is the 0. So we can put a box around this, and this will correspond to the minimum. And then the largest output is the 5. This corresponds to the maximum. Now, what we notice here is that the minimum does occur on an interior point. The maximum occurs at an endpoint. So now we can say the maximum of y is, just stating it by definition, is 5. And we know it occurs at -1 in one place, right? And the minimum of y is what? 0. So again, many times in the homework, you will state the ordered pair, because it is good to know where the actual max or min occurs. But by definition, the maximum of y is 5. The minimum of y is 0. That is, the maximum value of the function is 5. The minimum value of the function is 0. So now what you can see, and I'll just note here, we've got Fermat. So all of this is Fermat. The continuous part here, checking the endpoints and all, is what provides, or that the reason to provide or to do that is provided by EVT. So the provisions of the theorems are what are important to us here. That is, we do a combination. I call it the combo, with a continuous function on a closed bounded set or closed set. That is an interval that contains its endpoints. Now, that's normally what we're working with. Of course, closed sets don't have to be connected, okay? The closed set could be the union of two closed intervals that aren't connected. So don't think that only closed sets look like this. That's just one type of closed set. But that will be usually what we have at this point in our education in the calculus. But as you get into more mathematics and more topological ideas, the flexibility of closed will often change and provide more detail for your computations. Okay, so we've got that. Let's look at another example. Just remember, we're not doing really any new mathematics. We're doing the same stuff we have been doing. What we're doing now is just applying theory of the derivative to get more information. Before, we didn't have the max and the min, and we're going to look forward to being able to use the derivative to do many other things. Now, here's another example that I think you will find useful. Now, the first one I'm going to do, I'll do another algebraic example, but I just want to do a simple trig example that would, I don't think is going to be a surprise. So what we want to do is compute, then I'll go back to the algebraic one, compute absolute extrema. So this is the way the author or a textbook can say, find the max and the min, but not confuse you with relative. You know, they could say compute relative extrema, or they can say compute absolute extrema. Remember, the absolute may not necessarily exist, but if the problem says compute absolute extrema, they will exist. And at this point, you're going to be looking for what? A continuous function on a closed bounded set. So don't be bothered by the word absolute. Think of it as actually more information that clarifies things. And then when you see relative extrema, you're like, oh, okay, that's going to mean, a local extrema. But just remember, by definition, an absolute max is also a relative max. You get that for free. So you can characterize things however you need to get the results of a theorem. But what's important now is that if we're going to do this, we're going to hope that we have the correct hypothesis to do it. So here's a very straightforward example, but I think it's very interesting. We have f of x is cosine of pi x. And we have, in this case, a closed bounded set. This will be a little surprising. That is, the closed bounded set is 0 to 1/6. Kind of small. So we look at that and we're thinking, okay, well, this is interesting. I mean, we've got the cosine function, and the period is just 2 pi divided by pi, which is 2. So we've got a compressed period. So the period, just thinking about trigonometry, is just 2 pi divided by pi, which is 2. So that's interesting. And we think about this function, the cosine function at 0, and just picturing the cosine graph, it starts to fall. So it's actually a decreasing function. So we're thinking, we could probably intuit the max and the min in this case, just thinking about a trigonometric graph. But we want to use the theory to say, okay, let's just nail this down, and let's not think about a picture that may have been drawn incorrectly. I mean, I will tell you this, the pictures that you use for sine and cosine in your prerequisite courses were correct, but they were pictures based upon textbook examples. And then when your professor would say, okay, here's how we define this function, this is what it looks like. It has many nice properties, but now in the calculus, we're going back and we're seeing why these functions have these particular shapes, why they are continuous, now why they're going to be differentiable, which we learned in the previous chapter. And now we're going to get all the other aspects about increasing, decreasing, and shape. So it's good that we got good pictures before, but now we're going to verify that those pictures are actually correct. So first, what we want to do is the following. We've got a continuous function. Notice f is continuous on the given set. I mean, it's continuous for all real numbers, but certainly there. So this is the EVT. And it's also differentiable. So, I mean, that we're going to get from I anyway for free, but we definitely have the EVT. So we can say f of 0 is cosine of pi times 0, which is cosine of 0, which is 1. Okay, so now we can just say here, we've got the combo input of 0, output of 1. Not surprising. I mean, it's just the cosine function. So we know it's well behaved, but it has some really interesting properties. And when the sine and cosine are only shifts of each other, you would think they would be more intimately related than they are, but whatever. So now we have f of 1/6. So we're just looking at the endpoint, see what we get, cosine. And now we just have pi times 1/6, or pi over 6. And of course, that's from our unit circle. That's the square root of 3 divided by 2. So now, again, we always enjoy the beautiful symmetries of the unit circle, which give us such powerful results. So 1/6 is the endpoint, square root 3 over 2 as the output. Now, when you look at this, you're thinking, okay, well, is there going to be anything on the interior? Doesn't appear to be, but we need to check. So now we want to say f prime, because we think the function is just going to be decreasing when we think about the new period of 2, and certainly won't have much time to do much else with that small of an interval. So now f prime will be the negative sine of pi x, and then of course times pi using the chain rule, the derivative of the inner function. So we get what? Negative pi sine of pi x. Now, of course, this is always defined, and of course we've kind of beaten that up too much. So we'd say, well, equal to 0. So this again is where we bring in the Fermat, because the Fermat is connected to the critical numbers of f. And so this would mean, of course, when is the sign equal to 0, that would mean pi x is just a multiple of pi, where n is an integer. But of course, the pi's absorb, and we have x is equal to n. So we just get what? Values of n, 0, plus or minus 1, plus or minus 2, etc. Well, the only thing that is connected to this set would be the 0, the plus or minus 1, etc. would not be in the set. The only thing we have is 0 element of 0 to 1/6. So what we're seeing is that the critical number that we get here has already been taken up by an endpoint, but that's fine. I mean, it just we just have we're going to have the endpoint extremum, so to speak. So now we don't have any extra. So at this point, no additional information. I mean, we just make that comment that we applied Fermat, and we have infinitely many critical numbers, but the only one that's, well, critical numbers, if we were taking a bigger set, we have infinitely many values of x for which we will have a horizontal tangent. That's how I should phrase that. But we only get one critical number, and we've already covered it here because it's an endpoint. Okay, so no additional information from what we have based upon the endpoint. So don't interpret this as this being a bust. It's not. It's just that we don't get any more than we already had with the endpoints. So now this implies we just take the largest value, which is 1. So f has a maximum, we'll just say it this way, a maximum of 1. F has a minimum of square root 3/2. That's not surprising because, you know how these look. I mean, this is, we just got what, 1 to 2. So 1, 2, you know how you do you subdivide, to get your 5 nice points, and then you've got your max, 0, min, 0, how we always did in our pre-cal class, because life was not as hard as it is now, but it was important stuff. So we had something like that. So now when you look at this, you basically would just kind of put in our 1/6 here. That's our 1/2. So we've just got this piece right here where it's just basically dropping off. So it's no surprise to us that the maximum occurs at the left endpoint and the minimum occurs at the right endpoint. So that we knew, and that's what the intuition was. But what we are grateful for is that the new theory is completely consistent with what we thought intuitively. Now, sometimes our intuition is not any good. I mean, we have to adjust it. We're thinking, well, it seems like it would be this way. Mathematics is not always completely intuitive. I mean, let's face it. When you multiply the additive inverse of 2 times the additive inverse of 1, you get a positive number. That's not intuitive. That's a theorem. And that is one of the many properties of the real numbers. So we can't always look at everything in math as being an obvious result. But what we can notice here is that our work in our previous class certainly supports the conclusion that we get here, because we always drew our cosine functions with this shape. So we're starting to see that this shape was, at least we're feeling that it was a good shape, that it wasn't something that we're going to have to do a lot of modifications to make more correct. Just remember, ladies and gentlemen, a graph is just a reasonable plot. Okay, we're not some computer generated deal where we're plotting 1,000 points and you've got this beautiful graph that it looks like a piece of artwork. Fine, that's not the key here. We want to use the mathematics to draw a reasonable graph that represents the graph in a way because we understand its characteristics. So this is a nice example, albeit straightforward, but very important. So the only thing that makes the problem harder is that we have more critical numbers. Maybe we have to work harder to compute the derivative, so there's more analysis. But the strategy is the same when we have a continuous function on a closed bounded set. Now, the last one that I want to cover is another algebraic function that is fairly interesting. Remember, the key, and I like the way the author sets this up by pairing, again, the EVT with the Fermat. So we've got a situation here. Let me go ahead and type this. We have the function g of x, which is 2x squared. So algebraic, x minus 6, or actually we can just call this a rational function. This would be something you would have graphed in your prerequisite courses. We find so much beauty in rational algebraic expressions. I mean, we can have a rational function or just a quotient of algebraic expressions when we're talking about horizontal and vertical asymptotes. And then we see how that blends so beautifully with the arithmetic of the calculus. So there are all kinds of problems that we can do. Now, in this case, we want to compute, I'll just write this out, compute absolute extrema. Now, remember, when you're working a problem, it may be described to you and you're asked to compute or to make a certain determination. Well, that will mean that you're trying to find absolute extrema of a particular function. And then reading the problem, you will have to decide what that function is. And then once you make that decision, you do the same steps we're doing here. So now, of course, we only have one real number for which this is undefined, which is 6, but that is certainly not in this set. So we have a rational function, which is continuous. So we have g is continuous. All this theory we did in the first chapter is so important. The first couple of weeks of Calculus 1 are pivotal, because that's where we get all the basic information that we use throughout the calculus and throughout mathematics and STEM. So g is continuous on -3 to 2. So that gives us EVT. So we know by EVT that there is a maximum and a minimum. And we're going to use the combination with Fermat to actually determine what they are. So now, first, let's go ahead and make these calculations. If you like, you can always check the endpoints. Let's think of it this way. It doesn't matter how you do this in whatever order, but once you have EVT, go ahead and check the endpoints. Do that first, possibly. It's not required. I'm just saying try it. Or you're like, no, I'm going to go ahead and get the derivative, do that first, and then I'll check the endpoints. What order you decide is up to you. Don't worry about the order. Just make sure you don't forget one of the steps. So f of -3 is 2, -3 squared, and then we have -3 minus 6. So now notice we've got a kind of interesting situation here. We have a -9, which is just a -3 times a 3. And then upstairs we have a 2 times a 3 squared, but of course the negative absorbs. So we get this. So you can just go ahead and write it out in the factors. And of course, copies of the 3's absorb. Well, keep going if you want. Notice it's like everything goes away. I stopped too soon, didn't I? So we just have what, 2 over -1, which is -2. So if you look at this particular example here, notice that we can write this as the pair. The input of -3 gives us an output of 2. So I will say that when you're working on examples like this, -2, when you're working on an example like this, always think about this, and then think about this in terms of the vertical asymptote. We have a vertical asymptote at 6, that is x equals 6 is a vertical asymptote. And then we would do a sign test. And of course, we'd have a variation in sign on either side of 6. But of course, the 0 in the numerator is to multiplicity 2. So we always have positive. So we're just touching, the sign won't change. So just kind of keep that in mind and make sure that this is all working out. So it makes sense in this particular case that we have a negative number here. Now let's go ahead and do g of 2. So we have 2 squared, and then we have 2 minus a 6. So that gives us a -4. So we can just do -2 times 2. And then, of course, here we just have a bunch of 2's. Same thing again, kind of an interesting little problem. So all of these 2's, I'll just do a bigger box here. So notice here we also get a -2. So this gives us 2, -2. So what's interesting about all of these examples here, and I won't say that this is good or bad, but I think what we're seeing in this particular example is that if this turns out to be important to us, we're getting the same value. And then we'll think about a graph and see, if this even makes sense graphically. Now let's do the derivative. So we want to think about Fermat. And of course, we can take the derivative. So let me just write here the Fermat part. So we have g prime. And if you like, you can factor the 2, and we'll just have x squared divided by x minus 6. The numbers always tell us what to do. They tell us what to do. They tell us how to factor so we can get easy results. And if we abide by the results, we're in good shape. Again, very, very, very straightforward. So now by the quotient rule, we'll get 2x times x minus 6 minus x squared. And of course, the derivative of the denominator is 1. And then downstairs, of course, we have x minus 6 that we squared. Okay, so we have 2, and then multiplying, we get 2x squared minus a 12x. Then we have minus an x squared. And then, of course, x minus 6 quantity squared. Very simple. Now, notice I'm dragging the 2 along. I mean, when we set this to 0, it'll just be gone, but I'm just computing the derivative. I haven't set equal to 0 because I'm focusing on the algebra. So now notice the 2x squared minus the x squared just gives us an x squared minus a 12x divided by x minus 6 quantity squared. So now, of course, we could just factor the x in the numerator. So this will give us a 2x times x minus 12 divided by x minus 6 quantity squared. Now, of course, we can set this to 0. So now at this point, we're like, okay, well, by zero product, we have x equal to 0. So if and only if x equals 0, which is in the set, -3 to 2. And then, of course, we get 12 by 0 product. And then 12, or 12, which is not in the set. Again, that's fine. That's fine. It's okay. It's just not in the set. So we don't use this. Again, when we're just thinking of critical numbers of a particular function, of course, 6 would never be if we were expanding to the largest possible set. But now what we can see is from this particular computation here, if we had the standard domain of all real numbers except 6, then we would have what? We'd have two critical numbers. They would be 0 and 12. Okay, but the 12 is not germane to this particular problem. That's the only reason we kick it out. So now we need to check 0. So g of 0, well, that's easy. So that gives us what? 2 times 0 squared divided by 0 minus 6. Well, of course, that's just 0 over negative 6, which is 0. So this corresponds to 0, 0. So now, when we look at this, we see that we have a maximum value of 0, and the minimum occurs twice, but we're just, only once. We can write where it occurs. Of course, the homework will sometimes ask you, do you get a double occurrence? Do you get a triple occurrence? So we could say minimum occurs twice, because of course EVT doesn't tell us, how many times a particular absolute extremum can occur. It just says that it must happen at least once. And then they could all be the same number. That we don't get much at all. So we can say, so of course we've got the 3 values here. Again, let me just go ahead and say this is also corresponding to the minimum. So you might need to type all of these, but if we are to summarize, we could say the maximum of G is just the bare bones. The maximum of G is 0 when we consider this set. The minimum of G is -2. So again, more detail giving the input, more detail giving the input, more detail giving the input. Okay, so remember when we actually do these types of functions, the derivatives are important, especially when we're trying to find absolute extrema on a closed bounded set. Now, I just wanted to make one more comment here, because we've got plenty of information here that just reminds me of what you did in pre-cal. So I'll just make a few comments here. So if we have g of x equal 2x squared divided by x minus 6. Notice this is weird. I mean, if we think about it in terms of pre-cal, we have the degree upstairs greater than the degree downstairs by 1. So we can look at this with some synthetic. So we can do 6 here. And then we've got what? 2, and then a 0, and then a 0, because we've got 2x squared plus 0x plus 0. So we bring the 2 down. So we get 2 times 6, which is 12. 12 plus 0 is 12. And then 12 times 6, that's 72. So we get, certainly don't get what we consider to be a 0 in this case. But notice now, this says this is the reduced. So we get what? 2x plus 12 plus 72 divided by x minus 6. So this is just using synthetic division to give us the slant asymptote, so to speak. So this would imply y equals 2x plus 12 is a slant asymptote. So when we think about this and we think about the BVs, well, what are the BVs? We're thinking about critical numbers, but if we think about BVs, where can the sign change? At 0 and what? 6. Undefined and the 0. That's what the theory that will still be with us when we graph functions in this class. So now you can think at least a very simple sign test, 0 and 6. Of course, now if we were to replace x with a number much larger than 6, that would be positive. So we have positive, and then we cross because of the multiplicity of 1. And then, of course, here we stay down because of the multiplicity, dual multiplicity of the 0, 0. So we just touch there. So we have plus, we have minus, and we stay minus. But that's starting to, again, we think about this, and we're like, if we think about the derivatives, we had a critical number at 12 and one at 0. So that's not a surprise right there. So now notice, just as a few extra ideas here, x-intercept, of course, is 0. And then, of course, the y-intercept is also 0. That is, g of 0 is 0. We already know that g of 0 equals 0. And that turns out to be in this case, a critical number. So now let's go ahead and just do a little inexpensive, what do they call it, sketch. So let's see here. We'll spread it out a little bit. So if you want, so that it doesn't get too big too fast, we'll say 1, 2, 3, 4, 5, 6. And up here we'll do a little bit different scale, but I'll go ahead and mark in the vertical asymptote at 6. X equals 6 is this vertical line. So x equals 6. And then for our slant asymptote, 2x plus 12. So we can do this in twos here. So we'll do 1 or 2, 4, 6, 8, 10, 12. So I'll do this in twos. So 2, 4, 6, 8, 10, 12, just to make the scale a little bit more reasonable. So let's see here. So when we put in 2, let me just bump up here, 14. So, of course, when we put in 0, we get 12. I'll mark that here. And we put in 1, we get what? 14. So I'll go ahead and sketch this. Look a little bit different because I chose different scales. So let's go ahead and graph is going to go off into the stratosphere here. So we'll just go ahead and dot this in. Okay, so this is what you did in your previous course. This was always kind of fun. So this is y equals 2x plus 12. So a y-intercept of 12, a slope of 2. And now we have a y-intercept of 0, or x-intercept, y-intercept right here. And notice, we stay down, we hug, and then we go this way. And then as we move out this way, we're going to have another slope, and it's actually going to occur at like a 12, but my scaling is kind of bad. So notice here, we don't have any driveways here, but we've got to hit this point and then go back down this way. So notice we have the limit as x approaches 6 from the left. Let me go ahead and write that down. Let me do this in blue. So we have the limit as x approaches 6 from the left of g of x would have to be what? Negative infinity. And then, of course, as we approach from the right, it has to be positive infinity, just to remind you about infinite limits and the sign test. So I just want to go back and look at some stuff we've done before, because this is going to open the door to sketching graphs. So we've got to hug this line, and then we've got to pick up this point and then head back downstairs like that. And then over here, we're pretty much doing the same thing. We're in the positive realm. So we have something like this. So maybe we get a little bit closer, and then we move up like that. But really, this horizontal tangent is going to be down here. And even though my scale is going to be bad, it's going to be around 12 right there, because we already figured that out. So when you do this graph and you compare this, we have a horizontal tangent here. Graph, I'm not Rembrandt, but we got a horizontal tangent here. And we also have a horizontal tangent at 12, which is here. Again, the scale's a little squanched here, but we have another horizontal tangent here. Okay, and that's actually going to define a minimum, and that's going to define the maximum. So what we're seeing here, if we just stick to -3 to 2, which is right here, we get all that we need, and we're seeing that the minimum occurs in this case at -3 and 2, which are endpoints. Again, scale's kind of bad, but the maximum right here occurs at a critical right here. So when we're only looking at -3 to 2, let's see, 1, 2, 3, about right there. We've got here the -2 and the -2. So scale's kind of bad, but we get the -2 at the endpoints as we have here. So this is really the part of the graph that we just analyzed right here. Kind of funny. I mean, we are doing a local argument, and we see that the -2 occurs at the endpoints, which is the minimum, and then the maximum here. So what you drew before was exactly on point. It's just that it didn't have this kind of detail. And what we're seeing is that since we have another critical number at 12, we see that horizontal tangent there, right there. Okay, so when we think about what we do with Fermat and EBT to a smaller set, we can compare it to what we did in our previous classes. So now you're thinking, is it going to be correct that the curve and the increasing and decreasing will also be verified, kind of like we have here? Because that's going to be the next few steps that we're going to have to consider. Because when you think about it, when you think about this example, we still have a lot of things that we're still like, I have a question about this. You know, why do we draw the graph this way? I know it's continuous, I know it's differentiable, so it should look smooth, but we've got increasing here and what appears to be decreasing here, and then decreasing here, and then eventually increasing. And what do the horizontal tangents have to do with any of this? So we're going to see how all that fits into the picture. So when you do this problem here, the very first thing you should think of is like, well, that's a problem we did in pre-cal. It wasn't very difficult, but when you think about it, all of the pieces that you need to put together to get a graph are actually simple by themselves, but all put together make for more complication. But everything depends on what? The arithmetic, the signs. The signs tell us everything. And then, of course, the signs give us the infinite limits. So I hope that what we've talked about today is edifying in the sense that now you see that all of the work we've been doing is now greatly impacting the further theory of the derivative. That is, when we think about what we've learned today, EBT and Fermat, we're thinking, okay, there's got to be more to the picture, because we now have to figure out what are the other geometric aspects that will provide more detail. That is, how are we going to get to the shape of the function? How are we going to get to the increasing, decreasing? And once we have that, does the second derivative impact any of this? And then we're thinking, at that point, we're like going to need to see, well, we've done infinite limits. Well, what about limits at infinity? How is that going to change anything? It looks like that's what we're doing in the problem we just did, but we just kind of assumed, you know, we're okay with this. So once we get all of those aspects covered, then we will be able to optimize functions with ease. Well, at least we'll know what to do, but the arithmetic and the algebra can be very difficult. And then once we've finished all of that and we move into some approximation techniques, then that's going to open the door to the antiderivative. So I hope this has been, like I say, has been edifying. We will continue with these types of concepts in the next few lectures. Okay, I'll see you later.